So example 2 says, let's use a differential to approximate the root of 33, okay? So this is actually kind of cool, I like this. So the first thing I want to think about is, well, what's the closest? What's the nicest value root 33 is near? And, I would say probably root 36. So this is, I'm going to think about root 36 as my nice point or my fixed point. I know things about root 36. And so then I need to sort of create a function so that I can actually use this differential formula. Like to figure out, okay, well, here's how much I'm deviating y by, so I need to find a function and find a derivative at the nice value, and then put in how much I'm deviating x by. So the function's going to be the square root function. I'm going to let my function be f of x, and I'm going to let my nice value be 36. Which means how much am I deviating by? I want to evaluate 33, which is 3 less than 36, so my dx becomes negative 3. So if I know what happens at 36, I can approximate the change at 33 based on this differential formula. So again, what is the differential formula? The amount y deviates is approximately equal to the derivative at your point of tangency times how much you deviated x by. So I do need a derivative. So remember, the derivative of the square root function is 1 over 2 root x. And I'm deviating from 36 to get to 33. I'm deviating by negative 3. And that's the key. If you listen to the prepositions, you're deviating from 36. So 36 is your fixed point. How do you get to 33 from 36? You go down by 3. This derivative is at that nice value. So the derivative would be 1 over 2 root 36 times this negative 3 is the deviation. That is 1 over 2 times 6, 1/12 times negative 3. So that's negative 1/4. And realize that that's not the square root of 33. This is how much you are going to deviate by the fixed value. And so we can say that root 33 will approximately equal root 36 plus how much did you deviate by, right? Again, we deviated by, plus dy, how much you deviated by in the y direction, which we found was negative 1/4. So we know root 33 is approximately equal to 6 plus negative 1/4. Or 5.75, right? And if you go to your calculator and calculate the square root of 33, you can see just how close. Let me go over here and pull up my calculator. You can see exactly how close you are to the square root of 33, which I think you're gonna be kind of surprised, maybe impressed. I don't know. I am, but that's because I love math. Okay, so square root of 33, oops, delete that guy, 5.7445. I mean, that's a pretty quick approximation. So I thought that was really, really cool. Okay, there's another example of a differential that you might need to do to help you do maybe a calculation without having to actually do the calculation, right? So 2.002 to the 4th power. Probably not what I really want to do, but it's probably going to be close to 2 to the 4th power, which is 16. So I'm going to identify my function. My function is a 4th power, a quartic. My value that I think would be really easy to evaluate and look at a point of tangency is 2. And then how much am I deviating from that point of 2? 0.002. And again, notice that this is more than my tangent line, so I've added it. It's positive. The last one was less than where the tangent line was, so notice that dx is negative. So that sign is going to matter. Okay, so again, thinking about the structure, or maybe thinking about what that formula is, the y will deviate approximately equal to the derivative at your tangent line times how much your x deviates. So the derivative here is 4x cubed. Don't forget to find the derivative first. Then the deviation is 0.002. Plug in 2 to our derivative. 4 times 8, right? 2 cubed is 8 times 4 is 32 times 0.002. So we get 32 times 0.002, Well, if I would have doubled 32, I've gotten 64, but move it 1, 2, 3 decimal places. So it should be 0.064. And again, that's not what the y value is, that's how much we deviate by the y value. So we could say, all right, we'll take a look and we'll say that 2.002 to the fourth power should approximately equal 2 to the fourth power plus your deviation of 0.064. And it doesn't matter if you deviated positively or negatively, you still are adding that quantity to your y value. So that's 16.064. And again, if you go to your calculator and you actually type in 2.002 to the fourth power, we would get an answer of 16.064096606. Really close. And again, the closer you are to your point of tangency, the more accurate your approximation will be. And sometimes that, like, you know, being accurate to within like 3 or 4 decimal places is accurate enough. Especially if you have a very complicated function where you might be spending too much time trying to figure out what the function is when an approximation numerically is all you really need. Okay. So then let's do one more example here in this video, and I know the bell's about to ring, so I'm going to apologize in advance. But this is a very common type of question on the AP exam where they don't even give you a function necessarily. Like, they may give you an equation of the derivative, or they might give you a picture of the derivative, and still ask you to use differentials to evaluate particular points. So in this case, they do tell us -2 is my point of tangency. And notice that these values are very close to -2. And here's the y value of that derivative, or sorry, of that value. Okay, so if we want to evaluate f of -2.3, well, we know what our function is. See, there's the bell. We know our function, and we know what our nice value is. So our x value is -2. We're deviating from -2 to get to -2.3. We're actually deviating by -0.3, right? It's smaller than the tangent line, that x value. So then, I'm going to use my differential formula. Oh, I'm within the page, that's fine. I'm going to use my differential formula. dy is approximately equal to the derivative at our tangent line times the differential of x. And so the derivative is up here, so we're going to put in -2. So -2 plus 12 is 10. -2 squared is +4 plus 1 is 5. And my differential is -0.3. So it's 2 times -0.3, which is -0.6. And again, this is how much you deviate from what the y value should have been, which is 4. So then we could say that f of -2.3 will approximately equal whatever f of -2 was, plus this -0.6. And we said f of -2 was 4, I believe, right? Yep. And you add the -0.6, which is 3.4. Okay? Similar idea with this, except for in this case, my deviation is actually +0.08, because that is a little bit bigger than our tangent at -2. So we would follow the same structure, same format. Y deviates approximately by the product of the derivative times how much x deviated. We already knew the derivative at 2. We could plug it back in. We get -0.6. So it's the same thing from before, times our differential in this case is 0.08. So we get -0.48. Oh, I take that back. Sorry, there's an extra 0. So it's equals -0.048. And then that's what we add to our fixed value. So f of -1.92 will approximately equal f of -2 plus this differential of -0.048. And so then, wow, brain fart. I'm like, wait, this is not lining up. And I hope you caught this mistake already. But I did. I was so worried about getting this done in the bell that I completely messed up. The derivative was not negative 0.6. The derivative was 2. How silly of me. All right. So I feel like saying like, this is how you know we're recorded in front of a live audience, because I made a mistake. Okay, so the derivative is 2. And then the differential is 0.08. I was wondering why that was negative as well as that one negative, which is 0.16. And so then that's what we add on. So f of negative 1.92 will approximately equal f of negative 2 plus this 0.16, which is our differential. Let's get out of there. And so then we say, okay, that's 4 plus 0.16, which is equal to 4.16. Huh, I apologize for that extra 37 seconds of time that I made a mistake and wasted for this video. Okay, so let me stop this video, and then we'll do another one for the more examples.